All right, let's get started. I started the recording a couple minutes late because we were getting the exams. If you have not gotten your exam, please feel free to come up here and grab it. Less for me to carry back over to the engineering building. Okay, so homework 6.4 has been graded. The solution should be posted. Homework 7 was due today, and that's your last homework in Engineering 213. Other than the bonus assignment, which is to do the course eval and upload. I don't know why it does that. Upload proof of submission. Again, I don't want to see what you did, but if you just show me a screenshot of your completed survey list, I'll add I'll add 10 bonus points to your homework average. And everybody got the at-home game, so you all can game out what you need on the final and so on and so forth. Anybody have any questions on that? Okay, so I graded the exam, and I got a little bit inspired with that to maybe do something a little different for the next couple of lectures, since it's our last time together. We have a final coming up. I want to go through just everything we've done in the class this semester, but I've always said that the way to learn statics is to do it. And if you want, instead of just this open-ended exam review session, which, by the way, I mean, if you have questions, that come to mind about the exam, feel free to, raise your hand and ask. But I prepared some problems for us to do together, if you want. The problems themselves are somewhat challenging. The idea is that if you can do these, you should have no problem whatsoever on the finals. These are way more difficult than what's on the final, but they're a good review of everything that we've done this semester, and it covers the key concepts that I think we'll need to do. We probably won't get through all of them today, but I can add a couple also on Friday to cover some of the later half of the semester. Does that sound good? All right. My thought is, if you're going to be here at 8 o'clock in the morning, let's make it valuable. Okay, so first off, the logistics. We're doing it in here, in person, on paper. It is about twice the length of a normal exam, and it is comprehensive, all right? It'll have about 8 to 10 short answer questions and about 4 to 6 computational problems. That's what you can expect. The exam is closed book, closed notes. You can have a formula sheet and a calculator, and I do think you should bring a straight edge. I think that would help. On the formula sheet, same rules as before. You can put anything you want on it. I am going to make a slight addendum to this. When I say collect them after the exam, what I'm going to do is I'm going to, as you're turning your exam in, I'll take a look at them, and I'll probably just give them right back to you, because I want to make sure that you have your formula sheets in your notes for later courses and whatnot. The finals I keep, but the formula sheet I'll let you have. I want you to have that back. You don't need to waste time on your formula sheet with properties of centroids or things like that. I will provide those on the exam if needed. Don't include any fully worked out problems, and make sure that you prepare it yourself, that you're not just snipping stuff out of the slides. Although at least these slides will give you a good little guide on what to put together. Here's the class, and here's what's on the exam. So first off, we started with the fundamentals. So make sure that you understand classical motion. Make sure you understand Newton's 3 laws. Make sure that if I give you the mass of an object, that you can compute its weight by multiplying by g, the acceleration due to gravity. Make sure that you can convert units and perform dimensional analysis as appropriate. And really the key math concepts in the class are algebra and trig. I mean, we did a little bit of calculus. We needed it to understand centroids, but really algebra and trig are where it's at. The first main exam was on particle statics. So make sure, and basically what that was about was adding vectors. So make sure that you understand the properties of vectors, that they have magnitudes and directions, that you can describe them in IJ or IJK notation. You need to be able to add vectors, and you need to be able to apply equations of static equilibrium to solve 2D and 3D systems. And so with that, it means you need to be able to solve 2x2 and 3x3 systems of equations. So I would make sure that you bring a calculator that can do that, because that might show up on the exam. This is exam 2 land. Exam 2, the star of the show is moments. So make sure that you can compute cross products and dot products. Make sure that you can compute moments in 2D and 3D. So the formal definition of a moment is R cross F, but the shorthand definition, and what we used a lot, let's say in exam 3, is to just take a force times its moment arm. There's also the aspect of computing a moment about an arbitrary axis, where you take R cross F and you dot it with a unit vector along the axis in question. Make sure that you can resolve force couples and generate equivalent systems in 2D and 3D. Take a bunch of forces and collapse them into a short or a small, manageable collection of forces and moments. Finally, rigid body equilibrium. Basically, the same thing with particle statics, only instead of just sum of forces, we also have sum of moments to deal with as well. And ultimately, the name of the game is support reactions. And I mentioned this on the recording I posted last night regarding the exam, but if there was any one topic I would urge the class to study, and we're going to probably do some problems Friday devoted to this, it's support reactions. Because if you get the support reactions wrong, then the truss analysis or the shear and moment diagram is not going to be right. So it's a really critical step in the analysis. Speaking of, excuse me, sorry, my voice is still restoring. Exam 3, the name of the game was centroids and structural analysis, so make sure that you can locate the centroid areas, lines, and volumes, and that you can compute the moment of inertia. Structural analysis, again, support reactions, big important step. Make sure that you can compute the internal forces in members of plane trusses using the method of joints or sections, and that you can draw shear and moment diagrams. The only real new topic is problems involving friction. So make sure that you can determine equilibrium conditions for objects in direct contact. So that is the content of the exam. That's what the exam is going to cover. The rest of this is just a lot of the formulas and equations that we've used throughout the semester. I'm happy to go through this in detail, but we've seen all this before, and I have this slide, this slide deck posted on Blackboard right now. Does anybody have any general questions about the exam logistics, about what to expect on the exam, anything like that? I'd be happy to address them. Yes?
I think for the short answer part, looking at the short answer questions on the other questions is a good idea.
It's not a bad idea. The other thing I would suggest is just to go through the notes. We did have certain lectures that were a little more content heavy than others. So like, for example, we had, let's say when we were getting up to exam 2, we had a lot of lectures that were about defining moments and defining the equations and cross products and dot products. And then later on, it was just, okay, let's just do a bunch of problems. So it might be worth it to focus on reviewing those types of lectures as well. So the lectures that were sort of earlier on in the modules listed on Blackboard. So for example, if there's the topic 2 on particle statics, maybe the first couple lectures as opposed to the last ones. Does that make sense? That makes sense, everybody else? But yes, I will say that the questions that you will get on the exam are very much like those that you got on the last 3. Other like open-ended questions about logistics, you name it. All right, since we're here together at 8 o'clock in the morning, let's do some problems. Now, I've prepared 3 problems. There's a good chance we won't get through them all. And I'm going to go ahead and tell you, these are among the trickier problems that I would give you. These are probably more difficult than some of the ones I've given you even on homeworks. But again, the idea is that if you can do these, you can do just about anything. All right, so let's start off with this one, okay? So the first thing I should mention is that I will say one thing, okay, if this helps. Bless you. I am not one to give a comprehensive exam out of order, okay? So the first problems are going to be about the first stuff in the class. The last problems are going to be about the last stuff we talked about. So, as an example, the last computational problem will be the one with friction. Does that make sense? So I won't put a friction one in the middle of the exam. I don't like doing that. So this is a early part of the semester problem. So I have a boom that carries a load P and is supported by two cables at point A shown. Now we know the tension in this cable right here is 183 pounds. And we know that if we add up these three loads, read this right here. This is a really key statement. I'll highlight it. Let me get my little pen here. Oh, I can't draw a straight line. We know the tension in this cable is 183 pounds. We do not know the tension in this cable, but we know that the resultant of the forces exerted at A must be directed along this line. Based on that knowledge, what is the tension in AC? And I'm sure some of you are like, whoa, what is going on here? Okay? Let me show you what's going on. So, a couple notes. This is a particle statics problem. In other words, here's point A. We have this P vector. TAB. And TAC. So I'm drawing this point right here. We have forces all going through point A. So this is a particle statics problem. So there's no moments. If you look at this problem and think I got some moments, you're doing something wrong. Okay? So that's the first note I would mention. The second note I would mention is this highlighted portion. Okay? How do we compute a resultant vector? Okay, well, this. That's how we compute a resultant, right? We sum up all the x components of these forces, the y components, the z components of all three of these forces, and we get a resultant vector. Now, with that, I want to read this highlighted portion in very significant detail. It says, we know that the resultant of the load P and these two forces, so if we add up these forces, we get a resultant. We know that that resultant must be directed along OA. Must be directed along OA. Along what axis is OA aligned? Say again? The x-axis. OA is along the x-axis. So, for R to be these two have to be 0, right? Because the resultant will only be along that axis. So those two have to be 0. So with that, we can do some work. In the first step, is to describe the vectors in 3D. Okay? And actually what I should do is make sure that we're clear. Describe the force vectors in 3D. Now, how do I describe a force vector in 3D? I first define its distance vector, divide that distance vector by its own magnitude, then multiply by the magnitude of the force to get the force vector. Okay? So let's describe AB and AC. All right? So AB. All right? So let's see. Along the x-axis, we go negative 48. Right? Along the y, that's vertical, we go up 29. And then along the z-axis, we go 24. Does everybody see that? So 48 along the x, along the y, we go up 24, or up 29, and then along the z, from here to here, it's 24. For AC, it's still, it's still 48i. Now our y changes. Instead of 29, it's 25. And now we're going negative 36 along the z. Is everybody okay with that? All right. So what we'll do then, determine the magnitude of these. And given the fact that we're just doing some review problems and that I know that you all can do these calculations, I'm going to do a lot of these computations for you. So when you chug this one out, you get 61 inches. So therefore, lambda AB is just going to be that. Now, in this problem, we know, let's be clear, all right? We know, so let's just remember a couple things. We know that a force vector is equal to the magnitude of that force times the unit vector, right? That's our base expression that we're using, okay? We know, in the problem, we know that the tension in AB is 183 pounds. It's tension AC that we don't know, okay? So what that means is, if I want to determine that force, I can go ahead and numerically evaluate it right now. Excuse me. So checking that out, I get, it's actually pretty nice. Comes out in nice even numbers. So that's one of my vectors right there. Do the same thing for the next vector. As I'm going along, is everybody following along? Is this too difficult? Everybody, I mean, if you have any questions, please interrupt me. So we determine the magnitude of this vector. And when you plug and chug this, you also get an even number. You get 65 inches. All right. So now we're going to do the same thing. The only thing is that we don't yet know what the magnitude is. So we're going to have to leave that as a variable. So what I'll do is I'll say I'll just do that. In other words, up here, what we did is we took the unit vector and we multiplied 183 times all these terms. Here, we're taking the magnitude and multiplying it times all these terms. We just don't know what the magnitude is yet. So that's why there's a magnitude inside every one of these. Now let's not forget, there are three forces acting through this particle, and one of them is P. So we have to describe that one as well. But P is really easy. He's just that. Because it's just a force acting vertically along the y-axis. All right, is everybody with me so far? Is this making sense? Tell me if it's not, please. Okay. So now what I need to do is I need to sum these vectors up in order to determine a resultant. Okay? So what I'll do is I'll sort of write them tabular, sort of. That's an I. And so what I'll do is sum each of these up. But instead of writing all this out, let's just be common sense about it. What we're going to get when we sum these up is we're going to get everything in this box, which is just going to be the sum of the forces in the x direction. Everything in this box is going to be the sum of the forces in the y. Everything in this box is going to be the sum of the forces in the z direction. That's what's going to happen. So I'll just say the resultant is the sum of the forces, which is dot, dot, dot. You know, whatever we get there. Now, let's go back to the very beginning of the problem. And I said that the resultant needed to be directed along OA. So what that told me is that the sum of the forces in the x direction is the only one that may or may not equal 0, or may not equal 0. But the others will. What are we trying to find in this problem? What's the unknown? TAC? Look at this. Look at the sum of the forces in the z direction. Wait, it's 36. That's it. That was a challenging problem. At least more challenging than what you would expect on the exam. But it does cover a lot of things that I kind of like. Writing vectors in 3D, summing resultants, so on and so forth. Let me stop for a second and see if you all have any questions about this. Any questions? You want me to keep going with this? Is this good stuff? Okay, good. All right. This one's probably not as challenging. It's pretty straightforward. But everything's at an angle. So we just got to be cognizant about some things. Now, the last problem was not a equilibrium problem. This one is. This one is a particle statics equilibrium problem. I'll say notes. it'll require a 2x2 equation solution using IJ notation. Now I will go ahead and tell you, you can actually get around using an equation solver if you use the law of sines and the law of cosines. I get the feeling y'all don't want to do that, so we'll do it the standard way, which is fine. So we'll start off with a free body diagram of particle C. So what that means is we need to draw particle C and all of the forces that are going through it. So tension BC. That's going to be a 25-degree angle, right? Because if I have a parallel line cut by a transversal, and I know that's 25 degrees, I know that's 25 degrees. Similarly, we're going to have a force like this. The AC. That's going to be at 45 degrees. And then lastly, we've got our applied load P at 60 degrees. So that's our particle. So we describe the force vectors. So a pile of junk times A, or a pile of junk times I plus a pile of junk times J. So how are we going to do that? Well, we know that the associated angle from the horizontal is 45 degrees. So we can do magnitude times cosine of 45 degrees, magnitude sine 45 degrees. But remember, we got to respect our signs. TAC points up, so the J component's positive, but it points to the left. The I component's negative. So negative, positive. TBC, on the other hand, they're both positive. Angle changes. Now for the applied load, we know the angle is 60 degrees. We know the magnitude is 500 newtons. They're both negative, left and down. So we need to sum these up. Again, what we're doing is summing the forces in the x direction, summing the forces in the y direction. But this is a static equilibrium problem. We know they both have to be zero, but both of those sums. So by down just a little bit. And again, they have to be zero. Now what I'm going to do is I'm going to write it in sort of matrix notation. DAC. There's our first equation. We scroll up a little bit so I can still see what's going on. So just move that over. Write it in matrix form. There you go. So I'm just doing bam, 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 and then those constants. And then you, excuse me, plug that into whatever solver you'd like. So if you use the Casio, it'll give you an X and Y of. So therefore, Let's see how we're doing on time. All right. We'll take a look at the next problem, but we're not going to have time to do it. We'll take a look at that one on Friday. But I want to stop for a second and see if this makes sense. Anybody have any questions on this? Okay. I want to take a look at the next problem. This is a weird one. So this problem, we have a plate. So what I'll say is, this is a rigid body equilibrium problem. And what we have is a roller here. So a roller only carries one reaction. We have a pin support here, which in 3D says carries all three. Then we have a cable here, keeping this plate up. We were given the plate has a mass of 100 kilograms. We need to determine all those reactions. But the weird part is that there is a moment about the edge of the plate. And I'll tell you, that's actually the easiest part of the problem. All you do is you use your right-hand rule and say that this moment is negative 200J. It's really easy. But we'll go through that one on Friday. Let me ask a real quick question. This one will take us about 15, 20 minutes. Is there any other particular types of problems you'd like to look at on Friday? Because I know what I want to do. I want to do a couple reaction problems. Seemed like that was what tripped everybody up on the last exam. Sure, we can do that. We'll do a quick one because that can take a little while. We'll probably do like a T-beam because that only has two shapes. Anything else? Because that'll be a good review of centroids as well. So we'll do a T-beam and a couple reactions. We probably won't do trusses and shear moment diagrams since it's so fresh in everybody's head. We just did it. This is more about the stuff we did back in the day. And if you think about any questions that you'd like to ask about the exam, like between now and Friday, please ask. Don't just sit here and let me do problems if you've got a burning question you want to answer. Sound good? All right, I'm going to pull the QR code up again. Get your exam if you haven't gotten it. That's all I got.